Hi, everyone. This is Rob Gray from Arizona State University in the Perception and Action podcast. In this presentation, I wanted to bring in a few topics to talk about perception in baseball, both from the pitching side and from the hitting side. And for me, this is one of the great big things we still have to unlock in understanding performance, right? And I think there's a lot of performance gains to be made. And I'm going to use the analogy of The Matrix, right? The movie The Matrix, because I think what we're doing in a lot of cases is we're training athletes to see the matrix, right? We're seeing, and for example, in hitting, we're training them to see what the pitcher wants them to see, right? The agents in the matrix. Whereas I think if we focused a little bit differently and we took more of an ecological approach, ecological dynamics approach, they could actually see through the guys, through the deception, the tunneling, and all those things, and actually perceive what's actually there, right? And this is something that that I've been thinking about for a long time, and really kind of changing my view on how this happens. So that's what I want to talk about today: perception, how we control our actions, changing the view about what a pitcher and a hitter needs, right, to control their actions, and thinking about training it in a different way. So I want to start by talking about information, right? So information is, perceptual information you get from your environment to control your actions. And of course, in hitting and things like that, it's mostly we're talking about visual information. Pitching, we're bringing in proprioceptive information, picking up information about your body movements, right? And I want to make a distinction, a very important distinction that Gibson made between specifying information and non-specifying information, right? So specifying information are information sources in the environment that directly give you what you need to control your actions, right? So this is a very complicated diagram from one of my papers looking at when a ball is approaching you. The easiest one to understand is the one below, right? When a ball is approaching you, the time it's going to take before it crosses the plate is equal to its size on your eye divided by the rate of size at which it's changing, right? That is a universal truth, no matter what kind of pitch it is, what the count is, right? That will tell you when the ball will cross the plate, no matter what, right? And this is commonly called tau, right? So the key point is with specifying information, perception is direct. I don't need any other interpretation. I don't need a process to understand what it is. Something in the information is directly telling me what's going on, right? And there's also a similar one, a bit more complicated, for knowing the height, for example, of when the pitch would cross the plate, right? All based on kind of the angles of information, right? So these are specifying information because they specify directly what we need to control our actions. The other main type of information is non-specifying, right? This is the information that can be used to guide a control of our actions, but we need to do some extra work, right? So if you're a batter and you see a pitcher throwing and you see the hump in the curveball, right? So you see the ball coming out high, you can pick up, okay, that's their curveball. That's information that can help you hit potentially, but it's going to take some other work, right? Just knowing pitcher, it's a curveball, right, doesn't tell you when it's going to cross the plate, doesn't tell you exactly where it's going to cross the plate. Similar, picking up the pitcher's grip, using probabilities like the pitch count or the situation, knowing what a pitch is going to be, it's a fastball, right, doesn't give you enough, right? It's a clue. It tells you kind of what generally you need to know, but you're going to need to do some more work, right, to get to be able to actually hit the ball, right? With the precision needed to hit the ball. So non-specifying information doesn't give you all you need, right? And for some reason in training and a lot of things, we seem to be overly focused on getting hitters to do this, focusing on the non-specifying. To me, this is seeing the matrix, right? It's seeing what the pitcher wants you to see. You're falling right into their hands, right, when you're trying to pick up the pitch type versus specifying information, right? So that's one key distinction. From this stems two different types of ways we can control our actions, right? If we're going to use non-specifying information, right, we're essentially doing what's called predictive control, right? We're trying to predict what's going to happen in the future, right? So if I know that a pitch is going to be a fastball, I'm going to use that information to try to make a prediction about where it will be and when in a variety of different ways, okay? And so the assumption often with this type of control is, right, the idea of why we need non-specifying information like the hump and the curveball, the count and things, is because the information actually in the environment is not good enough. It's impoverished, right? So we need to do some processing, some predictions in our head to be able to control the bat. And I kind of, in a recent paper, a review paper I did, I tried to formalize this, right? So here's one way that we could use. So you could use situational probabilities from the count and the sequence, advanced cues from the pitcher's delivery, their grip, their body language, and then information when the ball is actually flying in the air, like the hump. And you're going to have to put this into some model in your head, right, to calculate, right? Because knowing a pitch is a fastball is not enough to hit, right? You need to know exactly where it's going to be. So you put all this information in an internal model, you make a prediction, you use that prediction to say okay, and I know the ball is going to be here in 0.2 seconds. I generate this kind of ballistic movement, right? This ballistic repeatable swing to get the ball to the bat, right? And I also give myself an option to check my swing later on. So that's kind of one version of predictive control. Another one is so we're using indirect perception. We don't know we're using this non-specifying information. We're making a prediction, and then we're programming an action. This is very much the traditional way, accepted way you hit, right? Another way we could do this, right, is we could have a big pitch recognition stage, right? So we're using all the same information, the hump and the curveball, the count. We're going to recognize, oh, that's a fastball. We're going to have kind of a stored memory of trajectories for each pitcher, right? And we're going to match it. Okay, that pitcher's fastball does this. And then we're going to use that to hit. And again, we're programming, right? So this is all predictive control. It's starting with the idea that the information from the ball's flight and the pitcher's movements alone aren't good enough. So we have to do this processing, this recognition, this, and so on, right? As I said, this has been the dominant idea. And from this stems some implications, right? From this, I think this builds the idea that we want to build a repeatable swing, right? We want to hit off a tee, focus on our technique, right? Because what we're doing in this model is we're essentially programming the swing and then unleashing it, right? And after we start it, we're not going to really do much else, right? Because we're making a prediction about the future, then we just have to put that into the program that generates the swing to get there. We're going to put a lot of focus on pitch recognition, on picking up using the probabilities, using this pitcher's tendencies. We're really training what I'm going to call categorical perception, right? We're trying to take this complex environment of a pitcher throwing a ball at us, and I'm going to talk about the other side of this shortly. And we're trying to put it into categories, right? That's a fastball. That's a curveball, right? We're going to train. We want to minimize the variability, right? We're not in this kind of model. We're not really making adjustments when the pitch is in the air very much, right? We want to kind of minimize that. We really want a very much repeatable swing. And this kind of allows for decoupled and out of context training, right? If we focus on pitch recognition, we can sit there with an app and try to recognize pitch types without actually swinging, right? We can focus on our technique by hitting off a tee and soft toss and like that. Right. So this is kind of the traditional way that we think about how we use information to control a swing. The alternative model, and the one that I like to, champion, based on kind of a lot of my research and changing my mind on things, is prospective control, right? So prospective control is what we're going to do in that is we're going to use information that's currently available in the moment, not some stored knowledge about the pitcher's tendencies or the count, right? We're not going to make any predictions or processing. We're just going to link our movements to information in the environment, information specifying information in the environment, right? In what's called prospective control, right? And let me give you a few examples of this that are relevant, right? So this is work by what's commonly called now the required velocity model. Imagine you're catching a line drive. So you're standing there in the field, a ball's hit directly to your side. You need to move your hand to the side to get the ball, right? The traditional predictive way that we would do this, right, is the ball's flying through the air. You use information about its flight, right, to predict where it's going to be and when, right? That's predictive control. Then I generate a ballistic hand movement to get to that spot, right? That's predictive control. The alternative, prospective control, and it's really outlined nicely in this paper, is that we don't really actually need to do that, right? We actually don't need to predict where the ball is moving because we can establish an information movement control law that will satisfy our goal, right? And the law is shown here. If I control the lateral movement of my hand, the acceleration of my hand based on the gap between my hand and the ball divided by the time to contact, which we can use as the tau variable I showed earlier. Basically, if I keep this relationship true, right? So if I adjust my hand movement to keep this relationship true, my hand will arrive at the same time as that spot as the ball, the ball, in the same place as the ball, right? I don't ever actually have to know where the ball is going or when it will get there. I just have to establish this relationship between my hand movement and the ball. Another example that's commonly been talked about is catching a fly ball, right? If you're an outfielder and the ball's hit up in the air, one way that you could catch it is you could stand there, look at the ball, predict exactly where on the field it's going to land and when, and then run to that spot. That's not what fielders seem to do at all. Fielders seem to, again, couple their movement online. So what we're doing, instead of predicting and making a programmed movement, we're continuously controlling our movement online based on some information. For example, the angle of the ball, its optical acceleration. There's lots of models of this if you're interested, right? So catching a fly ball seems to be another example of prospective control. Instead of predicting and programming, we're coupling our movement to information available in the moment, establishing an information movement control law. I'm going to control the direction I'm running based on something in the about the ball's flight, right? So we're using information in a very, very different way. So instead of trying to predict the future, what the common phrase that's been used in right now, Bootsma coined this, is that what the batter is doing and the fielder's doing or the pitcher, we're controlling the current future, right? So what we're doing is if we keep this relationship, right? So the easiest example is to understand is the bearing angle example. If you have a ball coming and you're moving this way and the ball is moving that way, if you keep that angle the same, you will catch the ball no matter what. It's called insects use this. People use this to steer ships, right? It's a very universal fact, right? If I move to keep this angle between myself and the object, no matter what it does, no matter what I do, if I keep that angle the same, what's called the bearing angle, I will intercept it no matter what. So I don't need to know how fast it's going, where it's going. All I need to do is keep this relationship true, right? So this relationship between my movement and the information in the environment is telling me about the current future, right? It's telling me if I keep this hold, I'm going to intercept the ball. If this angle is getting bigger, I'm not going to intercept the ball. So my future, it won't achieve my goal, right? So that's what we mean by the current future, right? Establishing this information. Let me show you some examples that seem to be consistent with this idea of prospective control using information online in the moment, and then we'll talk about some training implications. So this was a study on pitching, right? A really interesting one by Matsu in 2020. What they did in this study was a really interesting thing. They took a bunch of different deliveries from pitchers, right? So they had them throw 10 fastballs, right? And what they did was to establish a model, kind of a kinematics model between the location the ball ended up and actually the release. I think it was the release point and the kinematics of the movement, right? Your elbow angle, knee angle, and so on. And what they compared, interestingly, were conditions in which they established the relationship between your release point and the joint angles from one delivery, right? Versus what happens if I look at the relationship between your release point, but instead of taking the angles from all of the one particular delivery, I'm going to take your knee angle from your first one, your hip angle from your second, your elbow angle from your third, your wrist angle from your fourth, right? They call that random reconstruction, right? What this does, right? If the goal of pitching, right, is to have a perfectly repeatable delivery where you program something, then you just let it go and execute, it shouldn't matter which delivery I take your elbow angle from, right? It should be similar every time, right? And certainly it shouldn't matter that it shouldn't be any way related to your ankle angle on a particular trial. Okay. But if these things are working together continuously online, which you expect in perspective control, you expect a very big difference, right? Because your shoulder angle on any individual throw is going to be related to your elbow angle on that throw, not on some other delivery, right? So that's what they did in this study. And what they found interesting, this is showing the variability in your release point, and the variability in the release point was lowest when you took the point, all the joints from one particular execution, right? When you scrambled them, did this random reconstruction, the variability went up, right? Which suggests what's happening here is covariation, or what we commonly call a motor synergy, right? Your elbow and shoulder are working together, right? Continuously adjusting online using information, presumably proprioceptive information, to get the hand to the right place. Okay. So that seems to be what's going on. In batting, this is a model from that same paper that I put forth to talk about a perspective control model of batting, right? So what I'm arguing here is the batter's not using predictions about where the ball is going to be. What they're doing is they're coupling their movement, right? In the first part of the swing, when you're doing the weight shift and the stepping, you're coupling your information, your movement, your rate of your body and bat movement to information from the pitcher's body, right? For the pitcher, you're actually looking at the gap, the closure to the release point. Then as the ball comes in flight, we're using specifying information about the ball's time to collision, its direction it's traveling, to control my body movement continuously again, right? So I'm never predicting where the ball is going to be and then executing a movement. I'm coupling my movements, right, to the movement of the pitcher and the ball, right? So that's a very big difference from what we commonly think is going on, right? We commonly think you're just set it and forget it. Like you just let go. It's like firing a cannon, right? So the analogy I like to use, and I have a book coming out soon that I'm going to talk about this. Analogy I like to use is in predictive control is firing a cannon, right? You do all the work in aiming, planning, what I'm going to do with the cannon, light the wick, and the cannonball's gone, right? You can't do anything about it. This type of perspective control is like a guided missile, right? I'm just going to fire it off, maybe not in the perfect direction, but when it's in the air, I can adjust it, right? And so what this is the online perspective control. And what evidence do we see from that? Well, I've seen this a lot recently in my studies looking at batting training and batting and looking using force plates to look at the timing of the different phases of the swing, the timing of when you land, when you shift your weight. And what I shown here, this is what we expect in perspective control, right? So these are the standard deviations from swing to swing of a batter, the timing of their landing, the timing of their forward weight shift, timing of when the bat starts moving, and when the bat gets to the hitting zone, right? And what you can see here is we get a reduction in the variability, right? We get, as we go along, the action is getting more and more precise, right? We call this sometimes the funnel of variability, right? This can only happen if somehow the batter is making adjustments while the pitcher is moving, while the ball is in flight, right? If I just pre-program a movement, there's no way it can get more precise after it starts, right? That's like a cannonball changing direction in the air, right? There's no way that can happen unless I have a guided missile, right? So we need to train our batters and pitchers to have guided missiles, right? Not cannonballs, not just launching an action that you pre-planned, being able to tune into this information and control it online, adjust online. Okay, so that's evidence there. I also found very strong evidence of these motor synergies between um, the looking at, if you look at the weighting timing of weighting the forward versus backing weight shift from swing to swing, they're strongly related to each other, right? So if I shifted my weight back a little too early, I adjust my forward weight shift accordingly. Like they're working together. They're not just pre-programmed values, pre-programmed swing where we're trying to get rid of all the variability in our swing. This variability is actually functional, right? It's allowing us to adjust online. It's giving us this guided missile, right? We're getting these functional couplings, right? So for me, this is one of the keys to, improving performance both on the pitching side and the hitting side, right? Going from this kind of predictive control model where we set it and forget it cannonball to tuning into information that allows us to control online, adjust and control prospectively, using giving us the guided missile analogy. So how do we learn to control movements this way, right? How do we learn to develop prospective control instead of predictive control? Okay. And really, this is captured in a very different theory of learning called direct learning proposed by Jacobs and Michaels. And the idea is that it's a very different viewing and learning. Learning is not an accumulation of knowledge, right? It's not learning all the pitcher's tendencies. It's not learning all the what counts and so on. It's establishing changes in these information movement control laws, how I'm coupling my weight shift to the movement of the pitcher and the ball. And basically, there's three types of changes that can occur as we practice and learn. And this kind of guides how we should be designing practice, right? So these are education of intention. Okay. So what I can do is I can change either my goal, right? So initially, as I'm a lesser pitcher, my goal could be just getting the ball over the plate, but then I can change my attention to being, hitting the outside corner. Then I could I could change the aspect of my movement I'm trying to control, right? In running to catch a ball, am I trying to control my acceleration? In pitching, am I trying to concisely control the release point, the release spin, the release angle, right? These are the aspects of my movement I'm coupling the information to. So changing these through experience is called the education of intention. Education of attention is when you change the information you're using, right? So going from using, a classic example we saw, I've seen in research, is using the distance of an object to decide how to interact with it, changing to using the tau variable, right? And the final one, the most one that kind of continues forever almost, is calibration, establishing the relationship between your movement and the information, right? Start adjusting how that's related to each other. So education of attention, right? So think about, a pitch coming at you, right? A ball coming at you, and, you're trying to time your swing, right? We could time our swing based on a bunch of different information sources. We could time our swing based on the size, right? So we could start our swing when the ball gets to a certain size on our eye. We could time it to the speed, right? The rate at which the size is increasing, or we could time it to the specifying information that actually tells us when it's going to be there, the time to contact, right? And research has shown that, this is a plot of, what we can do is create an information space, and we can create for different ball trajectories. We would expect different things. We can actually take a hitter's performance and look at what they're actually using, right? If you're using a visual angle strategy, this is where your swing should lie. If you're using the speed rate of expansion one, and then if you're using the tau one. And there's some really good work, and I apologize for the quality of this figure. It's a really old figure. There's some really good work in a paper by Smith and colleagues in 2001 showing that with practice, right, batters shift from using just an expansion rate or size strategy to you can get them to use the more effective tau strategy, right? What's the key to this? What's the key to getting a batter to tune into the specifying information that's going to actually tell them where the ball goes? Variability in practice conditions. That's the key, right? If you have a batter hitting off a pitching machine, always set on the same speed, have them hitting by a coach that's throwing the same stuff all the time, it's going to allow them to use these non-specifying information sources, right? You need to really push people to educate their attention to a different information source. And that's what was shown in this paper. Once they started switching the size of the balls in this study, that achieved that. Okay. Education of intention, right? Education of intention, one of the things that we can see that happens there, right? So remember, education of intention is not changing the information you're using, it's changing the aspect of the movement of your pitch, the delivery you're controlling, right? So in throwing a ball, like I said, there's lots of different things I could try to I could try to control, I could try to regulate, I could try to throw so I made sure my hand ended up at the same height all the time. or that I release the ball at the same launch angle, right? If I'm tunneling or something. Right? So there's different things I can intend to control. And a good way of understanding this is by looking at kind of the variability in the movement, right? And this is a throwing task. What they did in this task was to use a analysis to understand variability called an uncontrolled manifold analysis. Okay. The way that I like to illustrate this is, imagine you're giving a task where you have to push down on the surface so that the total force is 10 newtons, right? So the force in each hand is what you're controlling, and that's free to vary, right? I could use 5 newtons in each hand. I could use 10 in one hand, 0 in the other, and so on. And what allows us to do is to create a state space. There's basically a solution space, and you can do this. I'll show this for throwing in a second, where we have right hand force versus left hand force, and we have this area called the manifold, where any combination I use along here is going to allow me to achieve my goal of total of 10 newtons, right? So I can use 5 and 5, 10 and 0, 0 and 10, and so on. So movement along here, right? Movement away from here, right, is called bad variability, right? We don't want that. We don't want to move off this manifold, or it's sometimes called orthogonal variability. If I move from 5 in each hand to 6 in each hand, now the force is too large, right? So this is bad variability. This along here is good or potentially good variability, because it's satisfying my goal, right, without and allowing for me to take different solutions, right? So if I start at 5 and 5 and my right hand gets tired, I can move this way, right, and do more work with my left hand. So it's allowing me to adjust to the conditions and the constraints in the environment. This is what we saw in the perspective control, right? The two things are working together. My left hand and my right hand are working together. So part of what's involved in learning this education of intention is developing these motor synergies. And let's look at the results from this study. So the basic prediction we have, if you're using perspective control, you're developing these synergies, we should see an increase in good variability, adjustments that keep you along that manifold, and a reduction in bad variability, right? We're we're balancing stability and adaptability is another way to think about it. So what they did in this study was they trained people for throwing, right? They measured the joint angles. They were throwing at a target. Their errors went down with practice. We saw a change in the state space, right? So they're controlling different aspects of their shoulder movement during the swing with practice. And what this was happening, this is a graph showing movement extent. What you can see is the white is the good variability, the black gray is the bad variability. What you can see is it's not the true of everything, but what you can see is the ratio. If you measure the ratio between the two, right, the good variability. So overall, the variability is going down, right? You're becoming more consistently, but you can see the reduction in particular in some things is much greater for the bad variability in the throwing. So the way that the pitcher is controlling the shoulder, the thrower is controlling the shoulder, they're allowing for variations that keep them on their target, the good variability, these motor synergies. They're removing the ones that don't, right? So that's a big part of what we see through learning. Here's what I found in hitting data. So this is basically the relationship between the shifting in the weight forward and the shifting in the weight backwards when you swing. The basic idea is those two things have to add up to equal the time it takes the ball to get there, right? I have to shift back and forward in the amount of time it takes the ball to get there. So I can create this manifold with some margin for error. That's the pink in this black, okay? The black swings are what I found before training, right? So you can see there's quite a bit of variability. Each of these black dots is a swing. There's a lot of bad variability, right? These were high school hitters when I first started working with them. A lot of bad variability. They're going off the manifold. Their timing, their swing, the combination of shifts is getting them there too late or too early. The white dots are what's happened after training, after 6 weeks of training, and particularly training that focused on variability of practice to add constraints. What you can see is they're not getting rid of all variability. There's still a quite large variability in the timing of the weight shift from swing to swing, right? But now it's mostly in the good direction, right? They're mostly using adjust combinations that are going to achieve the goal and get the swing at the right time. And you can actually calculate these as well, right? So that's in changing the intention, changing these how your joints are working together, right? The last one we see is a change. I want to talk about a change in calibration, right? I think this is really important for batters. This is a study we did quite a few years ago looking at changes in bat weight, how people adjust, right? What we did is suddenly introduced a heavier bat. We saw people have timing errors, then adjust immediately. Okay. They got back their swing timing. Okay. What we found was that um, there was the change how people did this, how they actually changed their control law, whether it was by increasing the bat speed. One group did it by increasing bat speed. Another group did it by increasing timing. Right. So this calibration, this link between the information and movement, was done in different ways. Right. And what we found was the reason that people did this, right, is because of their own individual constraints, right? So people that what we did was use Terry Bahill's model of maximum bat speed you can generate. And what we found was that people that had really high bat speed could adjust by just increasing their bat speed, right? So they had capacity to expand, right? Whereas people that didn't had to adjust the timing, right? So again, we're seeing these changes in with practice and learning and adapting to constraints, right? And the important point here is not only is this shaped by the practice environment, it's shaped by the individual constraints of the learner, their strength, their speed, their range of motion, their bat speed, right? So this is where it's going to tie into the rest of the people, Franz and everyone else speaking, right? Those, if we increase those things, we're going to affect how people calibrate, how people change their movement control laws. So it's really, really important there. Okay. So I think the training implications for all this, from all this, right, is we want to, instead of doing this kind of categorical perception, this decoupled training where we teach you how to program a repeatable swing or make a repeatable delivery, we want to focus on in-context activities with significant variability that allows an athlete to explore these different information control laws, right? We could add constraints that educate the attention better to different information sources, right? A good example I have is from a recent study I published. I don't think I've included in here, where I tried to train batters with opposite field hitting, right? And what I did this primarily by using constraints of barriers and connection balls that any kind of swing where they pulled out earlier, like a pull swing, they would hit the barrier or the ball would fall out. So I added these constraints. What actually happened as a side effect of this was they actually started at swinging more at outside pitches and less at inside pitches, right? Even though I didn't tell them to do that. What happens was when you use the right kind of constraints in a variability environment, you can kind of push people to using this more specifying information, picking up these advanced information as opposed to telling them these categories. Okay. So I think we need to move away from categorical perception based on these kind of, this is a fastball, this is a curveball, to allowing an athlete at the environment to explore and learn to pick up the information, right? So I started with one science fiction thing. I'll end with another, right? The truth is out there. And by the truth, I mean, there's information out there that tells you what you need, right? There's information that out there, as complicated as a trajectories look when we look at GIFs on Pitching Ninja or something of a pitch, as complicated as those look, and with spin and things, there is information out there that you can tap into that will tell you where the ball is going to be or allow you to couple to your movements to get your bat to the right place at the right time, right? Trying to predict from that information, you're doing this categorical perception. You're making yourself susceptible to tunneling, all these other things, because you're trying to use this non-specifying information. If you can train a batter through variability, constraints, and everything else to pick up and tune into this more advanced information, right? They're going to be way more adaptable and adjustable, and they're not going to rely on trying to pick up, oh, that's a curveball, and then being wrong and making a terrible swing, right? Tuning in and adjusting and developing these information movement control laws, I think, is key to the unlocking the kind of abilities of both batters and to slightly lesser extent pitchers. But I think that we can do the same thing, developing this good functional variability, these motor synergies. Okay, so that's all I wanted to say for this. As probably most people know, you can find out more about me at the site perceptionaction.com, my the Perception Action podcast, and I'll do a plug for. Hopefully, I'll have a link for this soon. If you go to perceptionaction.com/book, I have a new book coming out where I talk about a lot of the ideas about ecological dynamics and how they, this new view of learning, right? The importance of variability, the importance of these motor synergies, right? Self-organization. I'm trying to bring all this in kind of a more understandable way for a good as a starting point for a lot of people. So it's going to be called How We Learn to Move. So keep an eye out for that. And thanks very much for joining me. If anyone has any questions or anything, I would be happy to answer them via email. If you want to connect some other way, that would be great. Thank you very much.